Hello, I'm Patricia Shaw, and welcome to the sixth instalment of the Robot Benchmark Programming Introduction to Robotics series. In this video, we'll be having a look at the Pit Escape Challenge. So, what's this challenge? Well, this challenge involves a BB-8 robot. I have one here to give you a sense of size. It's a nice little robot there. And this is based on the Sphero 2 robot with a head attached onto it. In this particular challenge, the BB-8 robot has got to escape from this pit that it's been placed in at the start by driving back and forth around the dish. And the challenge is to escape as quickly as you can. So let's have a bit more of a look at the capabilities of this robot. So this robot's quite different to the robots we've been driving previously. We've typically had 2 wheels, sometimes 4 wheels that we can drive around using differential drive controllers. And by setting different velocities to each wheel, we can steer the robot around. However, BB-8 obviously is a sphere, and so actually being able to drive this robot is a bit more of a challenge. In terms of the actual motors that the BB-8 robot has got, it has 2 motors inside the body and 1 inside the head. And these are specifically referred to as pitch and yaw motors in the body and the simple head motor. But what's this pitch and yaw? Well, it's easiest to think about this in terms of an aircraft being able to move in 3 different dimensions. If you think of the pitch, then this would be leaning backwards and forwards with the plane. The roll is therefore side to side, with the wings tilting side to side. And then the yaw is actually rotating around the z-axis. So pitch is rotation around the x-axis, so the y-axis. Roll is rotation around the x-axis, and yaw is rotation around the z-axis. So when we're actually driving the robot, then we have a bit more of a challenge, because we have to, if we wanted to travel in a particular direction, then we would need to be adjusting the pitch and yaw motors using a little bit of trigonometry to be able to drive that. So what about sensing with the robot? Well, unlike the previous robots where we've had infrared sensors to be able to see what's going on in front of us, in the case of this robot, what we have is a combination of gyros and accelerometers. I'll have a bit more of a look at what these actually are in just a moment. But essentially, inside both the body and the head, there's a gyro and there's an accelerometer. And we can access both of those, or all 4 of those, independently. These do measure angles, and so it's worthwhile just sort of saying again that these values that it's reporting will be in radians, not in degrees. So if you are more comfortable working in degrees, then there's a little bit of maths to convert them to degrees, but by default, they will be in radians. So remember, half a circle is 3.14 radians. And so we need to take that into consideration when we're evaluating and comparing the values. So what are gyros and accelerometers? Well, a gyro is a gyroscopic sensor, and that's looking at being able to measure how much an object is rotating on a particular axis over a period of time. And typically, gyros are able to sense rotation, and it's broken down over 3 different axes. So those 3 rotations, the yaw, pitch, roll that we had, it's described as the amount of rotation around the X, Y, and Z axes. It's worthwhile bearing in mind that this is counting or building up, measuring the amount of rotation. So if you're actually spinning on the spot, it doesn't reset when it gets to a full circle, or 2 pi radians, or 360 degrees. It will actually continue to increase past that full circle measurement. So potentially, if you're spinning on the spot, you're going to get quite high numbers. but it can still be used to work out what direction you're facing in on a particular axis. Whereas the accelerometer, as the name might suggest, specifically focuses on measuring acceleration. And what does this mean? Well, if you're traveling at a constant velocity, or if you're stationary, then an accelerometer would record 0 in that axis. However, if you're changing velocity, so say you're starting from stationary and you're accelerating up to a particular target velocity, then the accelerometer will record that increase in velocity and report that to you. And it'll tell you which axis, again, in 3 axes typically, that this is happening. And it's worthwhile remembering a little bit of physics here. So gravity is an acceleration towards the center of the Earth. And so an accelerometer will measure the acceleration of gravity against that for the vertical axis. Now, it's also perhaps worthwhile being aware that these gyroscopes and accelerometer sensors are very widely used in consumer electronics. If you have a smartphone, then quite likely that will, or almost certainly, that will have these sensors in there to be able to sense as the phone is moving. So you might be able to shake your phone to do something, or when you turn it over, it might do something. Or also, more recently, a lot of phones are responding to being dropped and potentially preserving some of the electronics by disabling things whilst it's actually being dropped. Cars also have these sensors in them. And of course, robots. So it's not just the Sphero BB-8 robot that's using these, but these are widely used in a large number of robotic systems and applications. And quite often, these are actually combined into a single device called an inertia measurement unit, or IMU for short. So if you see a robot with a specification saying it's got a 6-axis IMU, then that's essentially saying it's got a 3-axis gyroscopic sensor and a 3-axis accelerometer to be able to measure these details together. Because clearly being able to know how fast you're accelerating and what orientation we're in is particularly useful for a robot. So let's have a quick look at the challenge itself. Now, before we look at how to go about tackling it, let's look at the starting program that it gives us. So here's the starting program. As before, we're importing the robot and getting an instance of the robot. It's providing us with the maximum speed that the robot can actually travel at in any direction, maximum speed we can send to the motors. And then it's giving us just the pitch motor as a starting point. So we're able to get that body pitch motor from the robot and be able to start working with that. Now, the robot also has access to the robot also contains a yaw motor. So if you want to gain access to that one, then you could actually repeat this, changing body pitch motor to body yaw motor. By default, it's changing from position to velocity mode for controlling that pitch motor. If you really wanted to, you could use position mode for solving this, but it is recommending that we use velocity mode. The approach that this initial program takes is it will essentially alternate in sending the speed minimum, sending the robot to drive forward and backwards using just this pitch motor, alternating the direction alternating the direction at a set time interval. And so here they're creating a variable which is setting the time interval for how frequently to change direction. And to start it off, they're then setting it to drive forward for that that's maximum velocity. And we're keeping track of which direction we're heading using this forward true. We're then keeping track of what the current time is so that we know when this time, we can measure when this time interval has been reached. And that's taking place inside this while loop at the bottom. So we can obtain the current time where we're at within the simulation. We can compare that current time to our previous time, and check that against our time interval. So this is deciding if it's the right time to switch direction yet or not. And depending on whether we were traveling forward or reverse last, then we set the velocity for that pitch motor and switch the direction in which we're traveling and reset the last time. So if we have a quick look at that running, we can see the robot attempting to drive forward and backwards. Initially, it is going in a straight line. You'll notice that the head's wobbling all over the place. And actually, partly because of the head wobbling all over the place, it does end up wobbling around quite a bit as well and losing track of the direction it's heading in. So actually, one of the first things you potentially need to consider how to overcome is the fact that this head can actually interfere with the movement of the robot when we're trying to solve this challenge. In the instructions, it does give some advice on how to go about adding the body gyro sensor. So here it does give you the code for adding the robot get gyro, body gyro to it. If you wanted to add the accelerometer as well, it would be body accelerometer. And if you want to add the head ones, it would be head gyro, head accelerometer into there. And then you can access those using the gyro get values. It might be worthwhile at this stage just reminding you that if you do want to access the full API and guidelines for the instructions for what functions are available, then you can access it through the help and the WebOps reference manual. Specifically, you'll want to have a look inside the nodes and API functions. And then if we scroll down in here, you can see the gyro is there, the axes and how to interact with the gyro. There's also the accelerometer up at the top. And of course, you can get the robot down here as well. And that gives you all of the functions that you can actually interact with for the robot, and sometimes some examples of how to actually go about using those. So let's have a think about how we could actually go about tackling this challenge. Well, the first thing is having a look at that time step. A simple solution to start off with this particular challenge would be to adjust that time step. Now, ideally, as we drive back and forth, we're going to want to go a bit further each time, building up momentum in order to escape from the pit. So rather than having a constant time step each time through the loop, then we might want to increase that time step. But of course, we're not actually necessarily going to be increasing it by a fixed amount each time. The amount that we want to increase it by might also increase each time that we go through, we want to change direction. So the first simple step could simply just be to work with the time step and gradually increase that by an increasing amount each time you change direction. As I said, the head can interfere with the movement of the robot. So it might be that you do want to adjust the head or set movement values for the head to try and keep it on top of the body whilst it's driving, but that is optional. You might also want to, instead of simply relying on timers to say when to change direction, you could also make use of this body gyro to decide when to change direction. Or you could have a look at using the accelerometer to decide when to change direction. As you're climbing up the hill, you'll be slowing down as you reach the point where you do want to be changing direction. So that could be a way of doing it. And the gyro can tell you which direction you're facing in. So if you do start to drift off course, then that might be useful. And of course, at the moment, it's only giving you the pitch motor. By adding in the yaw motor, you might be able to try some alternative strategies for getting out as well. So for example, you could consider spiraling out, going up higher and higher each time as you build up momentum to get out of the pit. So there's a few different options there as to what you could potentially try to tackle this challenge, but hopefully that will help you to escape the pit in various different ways. Good luck and see you next time.